Hello, everyone. My name is Jasien, and thank you for listening. I'm excited to share just a little tidbit of just what I got to do when I was sponsored as a SSGF fellow. So especially this one little snippet of my work that I did is titled "Coupling of Microscopy and Thermomechanical Models to Explain the Extent and Location of Trip Product and Simulated Powder Bed Fusion Laser Beam of the titanium alloy Ti 1023." And this is a collaborative effort with a bunch of researchers from the Colorado School of Mines, as well as Argonne National Lab, private companies such as ATI, as well as the Sigma manufacturing divisions at Los Alamos. Just to give a brief little bit of background for those of you who aren't necessarily material scientists. So titanium is a material that has garnered some high interest, mostly because of its high specific strength. So that's its ratio of its sort of tensile strength to its density, as well as it can maintain these properties at relatively elevated temperatures. Yet with these possibilities comes also some drawbacks, such as its difficulty to machine, so the process in that sense, as well as its raw material cost. So that has limited it in the past. However, with the advent of new manufacturing techniques, such as additive manufacturing or 3D printing, the titanium alloys have actually become a feasible material, especially for the aerospace, defense, and energy sectors. There's one alloy in particular, which has really sort of dominated the research space and the exploration. That is officially called Ti 64, 6 weight percent aluminum, 4 weight percent vanadium, and that is classified within the titanium world as an alpha plus beta alloy. It's been extensively researched. There's really a good understanding of how you process it. How is it going to react at the sort of atomic level, as well as at the sort of mechanical property level. However, with this material, there's been some problems with it. So essentially, with additive manufacturing or 3D printing, you rapidly heat and cool your material. So what this does is create lots of temperature fluctuations, which can then cause some processing difficulties, such as residual stress cracking. So there's really a desire within the Department of Energy to really just understand how we can utilize other Ti alloys to get these benefits while sort of mitigating some of these cracking issues. The one class which has sort of shown the most promise is called metastable beta Ti. It's a separate class of titanium alloys which can retain a high temperature, the high temperature beta phase after it's rapidly cooled. So after you quickly cool it, it can sort of metastably maintain this structure. So this starting metastability can actually facilitate enhanced mechanical properties. One being what will be labeled as deformation-induced transformations. For instance, so in maybe a typical material, you'll see a typical stress-strain relationship might be as you strain, you hit some yield point, and then you sort of level off and fracture. However, with deformation-induced phase transformations, what can actually happen is you reach some certain point, which enough to trigger this deformation process, and you get a significant increase in your strain hardening. Not strain hardening, in your work hardening. And so what that does is you get essentially improvements in ductility and damage tolerance over maybe a typical relationship. Additionally, with the metastable structure, you can actually get significant amounts of these secondary phases that can pop up when you process the material. So for instance, some researchers have found that just by simply heating and holding the material at a certain temperature, they were able to see upwards of a 500 megapascal increase in strength just over a material that was just printed and just tested. So there's really a good understanding, there's really a good desire to sort of see where this material class can go. So that's where sort of this research has sort of kicked off. So initially we wanted to really understand what was going on in these materials sort of at a smaller scale. So to do this, we performed very specialized experiments at the Advanced Photon Source at Argonne National Lab, using the schematic experimental setup sort of shown on the left here, where we are in one of the X-ray beam lines, and we bombard our material with incoming X-rays while we're melting and subsequently rapidly cooling or solidifying this Ti 1023 alloy. And so while the X-rays are incoming, it sort of allows us to hit an X-ray detector in the back. And so what that gives us is we can actually use this to sort of understand how these this melting and solidifying, how these responses actually sort of occur in this material. And so we did this for a variety of scanning strategies that are typical when you process additive materials, such as a single spot melt, overlapping spot melts, and then rasters and overlapping rasters. And just sort of shown on the right here, just some generic sort of typical X-ray images that you might see from one of these experiments. And so what this, like I mentioned before, what this was actually able for us to do was understand the response of this alloy specifically on the melt pool scale, sort of experiments that had not been able to be done at this level of precision, as well as this level of sort of accuracy in this material. And so we wanted to first sort of understand what was going on. So we started with our easiest sort of experiment. So a single spot melt, just shown up there, just to remind you what it looked like. And so when we look at it after it's solidified, when we look at it from the top down, we see our material that was melted here, and then our substrate that wasn't melted, and we sort of see what we would expect to see. And so when we want to look at this microstructurally and at the cross section, where it might be a little bit more representative of what's going on, so we sectioned the material and looked at it at the cross section. And so here is optical microscopy of spot melts for 3 different power conditions denoted in the bottom left of each image. And the actual material that was actually melted is denoted, or what we'd call the melt pool, is denoted with this outline red bar or red line. And so what we see is we actually see some distinguishing features that wouldn't necessarily suggest what we would think. We're seeing maybe some different phases, maybe something that's a little bit more needle-like. And when we zoom in on that, we can actually see it's a very complicated structure. It's not what we would expect to see from these alloys, which, if you remember, were supposed to be in one single metastable phase after they were rapidly cooled. And so the literature has actually shown that this material, when it's rapidly cooled, is actually single phase and actually behaves like we think. So it sort of causes us to scratch our heads and go, okay, what is actually going on here? And so what's actually occurring is that the material actually does solidify or sort of maintain that single metastable beta phase, which is oriented in the body-centered cubic atomic structure, just sort of outlined here. But when you apply some amount of deformation, what it actually allows it to do is actually then sort of transform into this martensitic lower symmetry orthorhombic phase. And so we didn't apply any external deformation to this material. So this sort of, again, further begs another question of where did this deformation arise from to cause this transformation? And so just sort of a schematic just sort of shown here is that these internal deformations actually arise from the solidification process, as well as some thermal contraction and things like that. So within the melt pool, we are solidifying and we're rapidly cooling. So we're getting actually some residual tensile strains in the melt pool, and this allows these originate from the thermal contraction of the melt pool. And then in the region surrounding it, actually, which I'll call the heat affected zone or the haze, we actually see that it tries to inhibit this material from contracting. So we actually get a residual compressive strain. So it sort of causes this behavior in the material. And so because we had some experience doing some previous modeling work, we wanted to see if we could dive into using some advanced thermomechanical models. So models that would predict maybe residual strains and stresses in the material, just to sort of see, hey, can we use these models to further inform and sort of confirm that this is what we're seeing and this is the reason that we're seeing it. So we used a thermomechanical model called SysWeld, and just sort of the sample geometry is outlined and shown here for both spot melt and raster conditions. And I'll talk about the rasters when we get there. And then we sort of used our information from our experiments, which got us a width and depth of these melt pools to sort of calibrate our models to be accurate in that sense. And so overlaying the simulations on top of the exact experiments, we actually see a very good correlation where essentially what's happening is as we increase the power, so moving from left to right of these samples, we see an increase in the amount of not only the this alpha double prime phase, or this martensite phase in the melt pool, but also this heat affected zone region. And we see that in the simulations, where as we increase our power, we see in not only an increase in the amount of area affected by strain, but we see sort of a larger magnitude of these strains. So this just confirms that this is a strain driven process, and that the increase in the amount of this strain induced transformation is a cause of the increased strains from the increase in power. And so with this sort of understood, we moved on to a little bit more complicated case where now we overlap a spot melt to sort of introduce maybe some thermal cycling into something, be more representative of maybe a 3D printed build. So here we have this case where we have two overlapping spots, and we zoom in on this boundary where we'd expect the largest amount of thermal fluctuations. And what we can see is that as we move up this boundary, which is the boundary between the first and the second melt pool, we see a gradual decrease in the amount of this alpha double prime or trip product. And just to sort of confirm that there's no other maybe microstructural or atomic features that are maybe inhibiting this, we perform some other characterization techniques which allow us to see grains as well as how those grains are oriented in space. And what we see is that there is this artifact here. However, that's not really affecting this gradual process. So to us, that sort of says, okay, maybe there's a reduction in strain going on. So when we go back to our models for this experiment, that's exactly what we see. As we move up along this corresponding boundary, we can see a reduction in the magnitude of the strains. So thus sort of showing us that this is a process where as we sort of heat it up to intermediate temperatures, we can actually cause it to go back into its other phase. So essentially, mechanistically, what happens is as we initially start with the beta phase, and because of that transformation, we get this alpha double prime phase, which we saw in the previous materials. But then when you apply some amount of stress relief, so in this case, a reduction from the thermal cycling, it actually relieves the strains enough that it can actually perfectly transform back into the beta phase. So our models were able to sort of validate our hypothesis based off of looking at this structure. Okay, so trying to just further complicate, just sort of understand how maybe we get a little more complicated, we added one more spot melt to the scenario just to see if we're going to see the same things. So we look at the same region of interest, that boundary between the first and second melt pool that we looked at before, and we sort of investigate that further, and we do see a reduction in the bottom of the melt pool to the top as we saw before. However, now it's no longer a gradual sort of decrease. It's actually an abrupt suppression. So we dove back into our models just to sort of see if they're going to show us something different. And they actually predict something very similar to the previous, where you would expect maybe a more gradual suppression or maybe a gradual reduction in strains. But because that's not what we're seeing, there's got to be something else going on with the material. So as we dive in to see if there's any sort of thing going on atomically or microstructurally, we see that this abrupt suppression actually correlates to this sort of denoted region right here, which is actually a grain boundary, a separation between two grains of material of different orientations. So when we think about that in the materials community, that sort of signals to us that there's some sort of orientation effect of these grains that are allowing a transformation or suppressing a transformation. So essentially what that sort of mechanism is called, it's called the Schmidt factor, which is essentially a way to sort of determine, based off of a specific sort of crystal plane in your material, are you going to be how easy is it going to be to transform when stress is applied. So for instance, what we did with this material is we looked at the martensite shear system, which is what is sort of dominating this material. And so we went and back calculated from our grain orientations what the Schmidt factor may be, where a higher Schmidt factor shows a greater propensity to transform, and then conversely lower would mean you wouldn't expect much transformation at all. So on the left here is a populated Schmidt factor map, where the sort of the darker colors are the higher Schmidt factors. And so what we see is that this grain that showed significant amounts of transformation indeed did have a higher Schmidt factor. So sort of just justifying to us that, okay, this is actually affecting what's going on. And so now moving on to a case that's a little bit maybe more applicable to an additive manufacturing build, we're looking at rasters or laser tracks on top of the material. And so we see a very similar material response, where we've got our melt pool denoted red up here, and then significant amounts of this trip product has formed in this heat affected zone region underneath the solidified material. And so what we actually, an interesting thing that we didn't see previously is that actually just sort of midway in between this heat affected zone, we see a very delineated region where we actually don't see any of this alpha level prime transformation. So it's an alpha level prime free region. And so when we dive into the models, what actually the cause of that is there's sort of as you transition from tensile stresses in the melt pool to compressive stresses, you actually get this sort of balancing point, this sort of zero stress point, which is what this correlates to, where there's not enough stress. There's actually zero or very limited amounts of stress to actually cause this transformation to happen. So these models were actually able to reveal and sort of show this to us. And so now looking microstructurally at what's going on, we looked at the beginning of this raster just to sort of investigate it further. And what we see again is a very delineated region that goes from non-transformation to significant amounts of transformation. So when we dive into some more characterization, we see that this region is separating two grains. And just to sort of correlate that to Schmidt factor, again, we again see that the higher Schmidt factor grain is the one that has transformed more. And so as we go into another sort of set of parameters, just to sort of see if we're going to see the same things, we get a very similar response now with a higher power and faster travel speed as compared to the previous raster. So as we investigate the first bit of the melt pool, as we did before, we see again a region of reduced transformation, and then abruptly there's a region of transformation. So as we dive into it, we would sort of expect that the Schmidt factor would probably correlate to that. But what actually we do see is that the lower Schmidt factor grain, so this orange grain correlating to this boundary, actually has the reduced Schmidt factor. So actually it's just sort of going back on what we thought, where now these lower Schmidt factor or these higher Schmidt factor grains are the ones that didn't transform. So this sort of caused us to go back and think. But if you notice, there's one difference in this sort of microstructure as compared to the ones that we have seen before, and that is a large amount of these smaller grains at the top of this melt pool. And so what that actually does it effectively decreases the size of these grains, where now you actually need an increased amount of stress or external or deformation to actually cause this transformation. Because to go from the BCC phase to this orthorhombic phase, your sort of atomic structure needs to accommodate these sort of strains in three principal directions. And so if it's a smaller size, it actually needs increased amounts to actually accommodate this. So essentially what we see is that as you decrease your grain size, you actually increase the stress necessary to cause this transformation. And then just to sort of validate that, we went back and performed another experiment with the exact same parameters, but now we remelted the top of it just to sort of try to get rid of those small grains at the top, just to sort of see if we would get back the response that we would expect. And that's and we do actually get it back. For instance, we see that here we've got a fully large amounts of trip in both of these regions, and we sort of see that these are a function of different grains. And we see now that we got rid of these very small grains at the top, and we've got a large range of Schmidt factors, just sort of showing us that as we remove these small grains, we're actually able to reduce our triggering strain necessary to then cause this material to retrip again. So in conclusion, I'd just like to thank all the various funding for this work, specifically the SSGF. They were a huge help in allowing me to sort of collaborate with lots of different peers at Los Alamos, as well as San Diego National Labs, which sort of helped system development of this work, just as well as just me giving me the personal freedom just to sort of go off and sort of pursue things that were interesting to me, research, and also things that I thought were beneficial to the community. So I'm very thankful for their funding over the past couple of years during my PhD work. So in summary, we've seen that this trip mechanism is influenced by both processing, whether that be the size of the melt pool, as well as the thermal cycling, as well as then microstructural features such as the Schmidt factor or grain size that I previously talked about. So based on this work, we've sort of identified that the accommodation of these strains and stresses in this material may produce crack-free parts and with tuned microstructures and properties that we haven't seen in any type materials before. Thank you all for listening, and I'll be happy if you shoot me an email. I'll be happy to answer any questions that you may have. Thanks.